everyone, this is K devender Reddy, Assistant Professor in Department of Electrical Engineering. In this video, we are going to discuss about power flow within a synchronous motor and power developed equation. So, the power flow diagram for a synchronous motor, the power input to the per phase in a stator, which is equal to Vi cos pi in terms of the total power input. P input is equal to root 3 times of VLIL cos pi, that is the power input to the synchronous motor. And out of this power input, total power supplied to the synchronous motor, the part of the losses we have. So in this stage, when you are connected the rated input path, that is root 3 times of VLIL cos pi to the stator, and in that we have losses due to armature winding losses, that is called as a stator copper losses, which is Ia square Ra per phase, and mechanical power into rest of the thing is mechanical power input, power in armature, which is equal to EBIA cos alpha minus phi. And in that we have iron excitation and frictional losses, and the rest of the power is given to the output side. So we can also see the power flow diagram, the AC electrical power input to the armature, that is a stator, and in that process when you convert that electrical energy into mechanical energy, that is called a gross mechanical power developed in armature. In that stage we have a losses due to winding resistance called stator copper losses, and after that the mechanical power developed we can call it as a gross mechanical power developed, and this developed power also will not connect it to the output directly. In between we have some sort of losses called iron, friction, as well as the excitation losses, and gross mechanical power developed minus these losses will be the mechanical power output for connected to the load. So this is a general the power flow diagram for a synchronous motor. Your input power will be converted into gross mechanical power. In between them we have a stator copper losses, and the developed mechanical power and output we have in that stage we have iron frictional as well as the excitation losses. Let us looking into the power flow diagram as well as the power developed by a synchronous motor. Let us consider the V as a reference vector, terminal voltage as a reference vector, and this is armature current. So this is a current Ia. This is Ia, which is lagging behind the terminal voltage by phi angle, and EB is a back EMF, and which is, let us mention this is EB1 and EB2. There are 1, 2, 3 instances where your load is changing. With respect to the load, your back EMF will be changed. So the back EMF phase angle will change. So the initially it will be of with respect to the EB2 it is alpha, with respect to the this is EB2 and this is EB1, let us say. With respect to the second stage, that is alpha minus phi, like the phase angle will change. Let us consider the things. V is the supply voltage, Ia is the armature current, and Ra is the armature resistance, alpha is the load angle, and phi is the power factor angle, that is phase angle. So input power, motor input power is VIA cos pi. Now this is in terms of per phase quantity. The total power input for 3-phase star connected synchronous motor is root 3 times of VLIL cos pi, or in terms of the phase values, that is 3 V phase I phase cos pi. Power developed by synchronous motor, the mechanical power developed per phase of the synchronous motor is PM, mechanical power developed is equal to back EMF EB, armature current Ia, cosine angle of between EB and Ia, that is cos alpha minus phi. EBIA cos alpha minus phi, that is mechanical power developed by synchronous motor for lagging power factor loading conditions. For leading power factor loading conditions, it is EBIA cos alpha plus phi. The copper losses in the synchronous motor is only takes place in the armature, that is the stator. So armature copper losses per phase IA square RA. For 3 phases, it is 3 times of IA square RA. By subtracting the copper losses from the power input, we obtain mechanical power developed by synchronous motor. So mechanical power developed by synchronous motor is equal to the input power supplied to the synchronous motor minus losses due to the winding resistance. That is root 3 VL IL cos pi is the input power and 3 IA square RA is copper losses. The total input power minus total copper losses will gives you the mechanical power developed by synchronous motor. To obtain power output expression, we have to subtract mechanical power developed minus the losses due to friction, losses due to iron, losses due to excitation. All these losses will be comes into the constant category. So we have to subtract mechanical power minus mechanical power developed or gross power developed minus all these losses will gives you output power. Net power developed by synchronous motor. So in this expression, we have assuming it as V is the supply voltage, EB is a back EMF, and alpha is a load angle, theta is the internal angle or impedance angle, and Zs is a synchronous impedance, and theta is equal to tan inverse of Xs by Zs. Mechanical power developed per phase, which already we know, EBV by Zs cos theta minus alpha minus EB square by Zs cos theta. The armature resistance is neglected. So if the armature resistance is neglected, your impedance becomes synchronous reactance and theta internal angle becomes 90 degree. Substituting these in above equation, we will get mechanical power developed is equal to EBV by cos theta becomes 90, cos 90 minus alpha minus EB square by XS, theta again 90 degree. So it is Pm is equal to EBV by XS. This is sin alpha, anyway it is 0. So mechanical power developed is equal to EBV by XS sin alpha. So let us derive the condition for maximum power developed. The value of alpha, that is load angle, for which the mechanical power developed is maximum, can be obtained by differentiate the mechanical power developed expression with respect to the alpha and equate it to 0. So we have that equation. This is the equation mechanical power developed under normal condition, that is by considering the resistance of the armature winding. So differentiate the equation number 1 with respect to the load angle, that is alpha, and equate it to 0. So d by d alpha of your rest of the equation, EBV phase by Zs into cos theta minus alpha minus EB square by Zs into cos theta and equate it to 0. So here EB V phase by Zs d by d alpha of cos theta minus alpha sin theta minus alpha and minus 1. Anyway, it is independent quantity of alpha, that is 0. So sin theta minus alpha is equal to 0 and theta is equal to alpha. This is a condition internal angle is equal to load angle, then the power developed by synchronous motor is maximum. Let us assume when armature resistance is neglected, anyway the theta becomes 90 degree because your impedance becomes synchronous reactance only. The corresponding torque at this instant is called as pull-out torque of synchronous motor. The value of maximum power developed can be obtained by substituting theta is equal to alpha in the mechanical power developed expression. That is equation number 1. Mechanical power developed is maximum when theta becomes alpha, that is a condition for maximum power. Substitute this condition in equation number 1, we will get EB V phase by Zs cos of here theta minus alpha, that is both are theta is equal to, you can replace with alpha, that is 0 minus EB square by Zs cos theta can be replaced by alpha. So it is EB V phase by Zs minus EB square by Zs into cos alpha. So EB V phase by Zs minus EB square by Zs when alpha equal to theta or theta equal to alpha. This is the expression for maximum mechanical power developed by synchronous motor. That is a condition when internal angle is equal to load angle alpha. So where if you neglect armature resistance, so from the equation number 2, if you neglect armature resistance, that theta becomes 90 degree again, right? So PM mechanical power developed is maximum when armature resistance is neglected. Only the first term will be remaining, that is EB V phase by ZS. Anyway, cos theta, that is cos 90 is 0. Second term is 0. PM mechanical power developed is maximum, that is equal to EB V phase by ZS, where your ZS becomes only excess synchronous reactance and RA is neglected. And we can also write down the expression in terms of by considering the armature resistance. RA is equal to ZS cos theta, XS equal to ZS sin theta. Substituting cos theta is equal to R by Z, we will get mechanical power developed maximum EB V phase by ZS minus EB square RA by ZS square. This condition you have to substitute in equation number 1. RA can be replaced with a ZS cos theta, XS can be replaced with a ZS sin theta, and cos theta is equal to RA by ZS. What actually the equation number 1? PM is equal to EB V phase by ZS into cos theta minus alpha minus EB square by ZS into cos theta. So anyway, this cos theta now replaced by RAZS, right? This can replaced by RAZS. EB square RA by ZS square we have. EB V phase by ZS when cos theta minus alpha becomes 1 when it is theta is equal to alpha, that is maximum condition. That is PM maximum when EB V phase by ZS when cos theta is equal to cos alpha in minus EB square by ZS into cos theta. This is equation number 2 actually. So substitute your assumption, that is cos theta equal to RA by ZS in this expression. You will get PM maximum is equal to EB V phase by ZS minus EB square by ZS. Cos theta now it is RAZS. So it becomes EB V phase by ZS minus EB square RA by ZS square. So solving the above equation in EB we will get, so this is in terms of the P maximum. So solve this equation, that is second order quadratic equation. You will get EB is equal to when we know the how to solve the equation second order quadratic equation, that you will get EB is equal to ZS by 2RA, that is minus B plus or minus square root of B square minus 4AC by 2A, that is the roots of the quadratic equation. So accordingly you can solve it and you will get ZS by 2RA into V plus or minus square root of V square minus 4RA into PM maximum. So EB is completely depend on excitation. The equation number, this equation number, that is it is 3 for example. The equation number 3 gives the excitation limits for any load for a synchronous motor. If the excitation exceeds this limit, the motor falls out of the synchronism, that is out of the magnetic locking. And later you have to know the condition for excitation when the motor develops maximum mechanical power. The condition for excitation when motor develops the maximum power. Let us find the excitation condition for maximum mechanical power developed by synchronous motor. So excitation will be controlled here. So you can derive the you can differentiate the expression mechanical power developed expression, that is equation number 1, with respect to the back EMF and equate it to 0, that is d by dEB of your mechanical power developed expression and equate it to 0. That is assume load constant, that is load angle I am assuming it as alpha, not del. Load angle is alpha constant V phase by Zs cos theta minus alpha minus 2EB by Zs cos theta is equal to 0. But theta is equal to alpha for maximum mechanical power developed. So Pm becomes P mechanical. V phase by Zs, theta becomes alpha cos 0 1 minus 2EB by Zs cos theta, it is equal to 0. Substitute your cos theta equal to Ra by Zs. So V phase by Zs minus 2EB by Zs square into Ra. So from this you can write down expression for Eb, which is equal to V phase Zs by 2Ra. The corresponding value of maximum power is V phase square by 2Ra minus V phase square by 4Ra. So you can substitute Eb. So it is V phase square by 2Ra minus V phase square by 4Ra. So this is the power flow diagram as well as the power developed by synchronous motor, the output power as well as the input power, and condition for maximum power developed as well as the excitation limits for the corresponding maximum power developed in a synchronous motor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.